Hi, good morning, everybody. I got question from a student about how to apply Thevenin's to EAC circuit. And I believe it's an important question, and we should be able in this class to use and implement Thevenin's theorem to all circuits, whether it's DC or AC circuit. So let me just remind you by Thevenin's. Thevenin's theorem is a powerful tool in AC circuit analysis and also DC. Okay, why? It allows us to simplify complex networks into an equivalent circuit for analysis. So by applying Thevenin theorem, we can replace the original network with Thevenin's equivalent circuit comprising a single voltage source like E Thevenin in series with a single impedance that will be Z Thevenin. This equivalent circuit represents the behavior of the original network. So in front of us, there's an example of AC circuit, and we wish in the end we'll have like one equivalent circuit like that. One source that will be E Thevenin, exactly as we did in DC. And it will be like a phasor form, of course, and in series with impedance. Impedance could be R resistant with inductor or capacitor, whatever, depends on the circuit. That would be Z Thevenin. In DC, if you remember, it was just resistant. So that will be the equivalent. You can put it in the box here. So that's the equivalent of Thevenin network that we try to find out. So you got to figure out the output terminal. The output terminal here where you put the ZL. So that's you can say that's if you put 2 points here, that's point A, point B. So that will be the output terminal. So I'm trying to find the equivalent circuit for this part. That would be equivalent Thevenin. And then after that, you can connect the impedance of the load. So the equivalent circuit, this equivalent circuit, represents the behavior of the original network as seen from two terminals, which in this one AB. In AC circuit, this theory is particularly useful for analyzing circuits with multiple components by reducing them to a simple form. By determining the Thevenin voltage, which is here called E Thevenin, and impedance, which is called Z Thevenin, we can easily analyze the behavior of the circuit and calculate various parameters such as voltage, current, and power across different elements. This simplification greatly facilitates circuit analysis and helps engineers and designers make informed decisions about circuit design, performance, and optimization in AC systems. And we're going to explain that in detail in this example, how to calculate the maximum power as we did exactly in DC circuit. Okay, so let's go ahead and start finding the equivalent circuit, or the equivalent Thevenins in this circuit. We know we need two elements: the equivalent impedance, Z Thevenins, and the equivalent voltage, E Thevenins. How we'll do that? We'll start with the equivalent impedance. To find the equivalent impedance of Thevenin, just let's take a copy of this circuit, all right? And I'll show you now how to do the impedance. Well, we don't need this information. First, you got to replace all the values of the impedances, because reactance given like 8 ohm capacitor will be minus J. So just all we want to do, find the equivalent impedance of each element. So that will be minus J, and that will be plus J, and the resistance 10 ohm stay as it is. Then all sources should be equal to 0. When you find the impedance, all sources should be equal to 0. Well, because I'm trying to find the impedance, right? So let's just write here, step number 1, find Z Thevenin. Well, how you put all sources voltage zeros means ES is equal 0, that means short circuit, and IS is equal 0, that's open circuit. So to make the short circuit, I remove the voltage source and I replace it by a wire. To have the current source equal 0, you just remove it, don't replace it. It's open circuit, nothing is here. Actually, you can remove the whole wire, open circuit. Second, of course, the load should not be connected to the point AB, so just remove the load. So always when you find the Thevenin, you got to remove the load. That's the first step, that before you do anything, remove ZL. That's supposed to be step 1. And step 2, find Z Thevenin. Now, if you look from this side, what can you see? We assume that there is a current. That's the way that we used to do. If we have current and this current flowing from the input here, it's not the input, but I mean from AB, the current will come to this node and will be divided into two. Will be divided to I1 and I2. So whatever connect to I1 and I2, they are connected in parallel and then will be in series with minus J8. So you can say that Z Thevenin, according to this circuit, 10 ohm is in parallel with J8, and the whole thing will be in series, means you are adding with the capacitor. So how to find the parallel? You multiply the product over the sum, and then you add minus J8. Doing that on the calculator, you will get the value for the impedance, which is equal to 3.9 minus J 3.1 ohm. If you want to express polar form, it'd be 5 angle negative 38.66 degree ohm. That's the impedance. So we did we found the impedance, the equivalent Thevenin's impedance. And now we're supposed to find what the E Thevenin, and that's, you got to pay attention to it. So to find let's just not forget, that's the Thevenin. And now we're going to find E Thevenin. We'll make a copy, still have it in the memory, I believe. That's the whole circuit. We'll remove, sorry, we have to remove also that's I mean, always remove the load impedance, and you keep the sources. Keep the source. You want to find the voltage across AB. If you can find the voltage across AB, that will be exactly E Thevenin. Well, I will write E Thevenin. Let me just write. That will be E Thevenin. You can use V or E, doesn't matter. So the voltage between the points AB, it's the Thevenin voltage. So of course the point B is connected to the ground. So your job now to find the voltage at node A, or point A. So you want to find the voltage here, all right? So try to think about the circuit now. You want to find the voltage across AB. In this circuit, you observe that you have two loops. This is loop, this is loop. So you think, can I use mesh current method or voltage node method? Both they can be applied. Both they can help you to find the solution. Try always to find the easiest. Well, I have mixed. I have voltage source, I have current source. You can try it home by converting the current source voltage source and use mesh. But here I'm going to use node voltage method. So I want to find the voltage at this node. Well, to solve this one, I would say this is node 1 and this is node 2. All right. And so my job now to find the voltage at node 2. Because the voltage at node 2 is the same as the voltage VA. How to apply the voltage node method? just so that use voltage node method. So you will say that the current at this node, the sum should be equal 0, or the input current equal the sum of the output current. So let me just assume any current in any direction. I'd like to assume it in this direction. That's called I1, and that will be called I2. For the current here, I don't have a choice, because you have IS and this open circuit other side. So the current IS will be just going in the node. No, there is no other branch that will be divided. The current IS stay here. IS will be like just flowing. You see, IS going there. There is nothing. It is open circuit. So just continue this wire going into the node. All right. So applying node, you will say the sum of the input current, which is IS, is equal the sum of the output current, which is I1 plus I2. IS, it is given. The value of IS is given in the problem as a phasor. Just let me make it phasor here. It's equal to 0.5 on angle 0. So you have 0.5 on angle 0 equal I1 and I2. How you find the current I1? I'll just make it here in simple way. That's node 1, and it's connected to resistance, which is equal to 10 ohm, and there is a voltage source. All right, ES, and ES, the value is already known. It's 120 on angle 0. All right, so I can make it now simple. You have one node, that's node 1, and the voltage at node 1 is V1, and you have a resistance which is equal to 10 ohm, and you have on other side here this node, the voltage ES. All right, and the current I1 is going in this direction. So what's I1? I1 will be equal to V1, because going from V1 to ES. So it'll be equal to V1 minus ES, of course all phasor, divided by the value 10 ohm. All right, plus I2. I2, just focus, that's I2 here, going in this direction. The voltage of this point is V1. All right, just let me just remind you, when you write the node 1, it means that the voltage at this node is equal V1. And the voltage here is 0 because connected to the ground, the reference point. So I2 is equal V1 minus 0 over 8. So that's for I2 will be equal to V1 minus 0 over 8. Oh, sorry, that's J8. All right, don't forget to. Okay, so that's J8. So that's the equation. Again, IS, it's current source, so it's going to be flowing in this direction. You don't have to make, we don't know the voltage here. If we know the voltage here, we are done. It's required to find the voltage here. Because somebody maybe think, why don't calculate IS by saying V2 minus V1 over. Yes, I can. But the problem, I don't know V2. And I already know the value of the current source. And the current source is flowing here, like that. It's just flowing there. It will be divided here, but till go to the node, it's the same current. Because the other side is open side. All right. So that's why I put IS, and this is the value. Now I just put the value of the VS. That's 0.5 on angle 0. And V1 is not known. And ES is 120 on angle 0. Divided by 10 plus V1 on J8. You can just ignore the 0. And actually, when you have 120 on angle 0, it will be like 120. Okay? You try to start to simplify this one. 0.5 on angle 0, it means 0.5 equal V1 on 10 minus 120 on 10, because 120 on angle 0 is equal to 120, plus V1 on J8. All right. I will start to simplify. I have 0.5 equal V1. I have two terms here. I have this term and this term. So have a common term. I'll take V1 as a common factor. What's left? You have 1 here, 1 over 10, and V1 over J8. and V1 is common factor. What's left? Minus 120 over 10, which is equal minus 12. Well, now I want to find V1. So you just can move negative 12, all of it. You just can move it there, right? So you have 0.5 minus 12 equal 1 over 10 plus j, you do it in the calculator, it will be equal to 0.1 minus j 0.125 is very simple. V1. That will make it, minus 12 when you go there will be plus, right? So you have 12.5 equal to 0.1 minus j 0.15 times V1. From this equation, you can find V1 by dividing 12.5 by 0.1 minus j 0.125. I did that, and I expressed in polar form will be 75 voltage, and the angle is 51.340 volts. That's the V1. So I got V1 here. All right, let me take a screenshot from this one to continue, because I don't like to be going up and down. And we put the values that we got. Okay. We just found V1 equal to 75 voltage. So V1 here, I can now put the value. V1 is equal to 75 on angle 51.34 degree. And IS, we know IS is equal to 0.5 angle 0 M. And it's required to find V2. That's our goal, because V2 is equal to VEB, which is the E Thevenin. So how to find that? That's simple. Let me just now, I will put it in simple form. You got V1, and you got capacitor minus J8 ohm, and you got V2, and you got IS. So how to find V2? How to find? Of course, if the current flowing in this direction, make it this positive and this is negative. And you know V1, it's positive here. Positive here. All right. So according that, V2 will be equal V1 plus the current times minus J8, according to the this simple circuit in front of us. This simple circuit extracted from this big one. So just you can focus on it. You have voltage here, you have voltage here, you have current in this direction, make it positive, negative, and this positive, negative, so they are connecting series. You are adding the voltage to get V2. That's why I say V2 is equal to V1 plus IS times minus J8. You know the old values. V1, already we got it, is equal to 75 in the angle 51.34 degree plus IS, which is equal to 0.5 on angle 0 times minus J8. In doing that on the calculator, find the voltage, it will be equal to 78 on angle 53. I round just the number. That's V2. Excellent. So now we have V2. V2, it's the same as VEB. It's the E Thevenin. So actually now we can write E Thevenin. We found E Thevenin. E Thevenin is equal to V2, which is equal to 78 on angle 53 degree. So we found the equivalent Thevenin. Why E Thevenin is equal to V2? Because, again, that's V2, which is equal to VEB, the open circuit voltage, which is equal to E Thevenin. So now we have the voltage, we have the impedance. You can now construct the the equivalent Thevenin. So you have one voltage source, and it's we call it E Thevenin, and the value of E Thevenin we found it 78 on angle 53. And also we found the impedance. Always we make impedance like a small box like that. Z Thevenin. And the value of E Thevenin that we found it's equal to 5 on angle negative 38.66. Or you can express it in complex form, and I will need it, so that I will just write it in this way. I like it this way: 3.9 minus J 3.1 ohm. It's the same thing. So that's equivalent. So actually the equivalent Thevenin, it's like a voltage source, and the impedance consists of resistance connected in series with capacitance, because they have minus J. And that's the open circuit, or the terminal AB, the output. So that's your Thevenin equivalent. Can make it in a box like that. That's it. And then you can connect the load if you like. If you are giving the value of the load, you can just connect it here, and we call the load the impedance ZL. And you can calculate the voltage if it's required. Let's say that you want to calculate the voltage VL. You want to calculate the current in the load IL. That's very simple. How you'll do that? Well, to find the voltage, you use voltage divider rule. Because you know VL, the voltage across the load, divided by the source, which is E Thevenin. Of course, everything is phasor, equal the corresponding the impedance of the load, ZL, over the total. What the total? Z Thevenin plus ZL. That's the voltage divider rule. So from that we can say that the voltage across the load is equal to E Thevenin times ZL divided by Z Thevenin plus ZL. It's the same thing we did with DC, but you just replace R by Z, that's all. In this particular example, VL will be equal E Thevenin, which is equal 78 on angle 53, multiplied by ZL. ZL is not given. Let's just give you value here for ZL. Assume that ZL equal to 2.1 plus J 7.1 ohm. Like you have resistance in series with inductor. All right. So ZL will have 2.1 plus J 7.1 and divided by Z Thevenin. We have Z Thevenin complex number 3.9 minus J 3.1 and plus ZL, which is equal to 2.1 plus J 7.1. Doing that, you will find that it's equal to 80 on angle 93 degree. You can check this in your calculator, see if you got the same result. So that's the voltage across the load. If you want to find the current across the load, it will be the same thing. You just you divide it. If you want to find the current across the load without even knowing the voltage across the load, you can just divide it E Thevenin by the total impedance in the circuit, ZL plus Z Thevenin. I'm not going to do it, just it's mathematical. I wanna focus now on something important. As we did with DC circuits, the question is, what is the impedance of the load if you connect it to the circuit? You can deliver the maximum power to the load. So now the question is, we have E Thevenin. We did that before in DC, but now we are dealing with Z. We have Z Thevenin, we have E Thevenin, and we need to select specific impedance for the load in a way to deliver here the maximum power. All right. Well, we know that Z Thevenin consists of resistance in series with an inductor, whatever we have, right? So how can you find the power maximum? Very simple. let me just write here. Z Thevenin, it's equal to R Thevenin plus J X Thevenin. Of course, X Thevenin can be negative, like in our case here. If you ask what's X Thevenin in our case, it's minus 3.1. I'm just writing general rule. And ZL is equal to RL plus JXL, and not XL. Yeah, load. That means that inductor L means load here, right? Don't just mix it up with inductor L load. To get the maximum power, or to deliver the maximum power, there is a condition. Remember in DC circuit, we used to say that the resistance of the load should be equal to the resistance of Thevenin's. When we have DC, you will say R Thevenin is equal R, I'm sorry, the other way around. The resistance of the load should be equal to the resistance of Thevenin. That's in DC, not here. That's in DC. Just to remind you. With AC, it's similar, but we have to make the circuit resistant. All right. How to make the system resistant? If you have the impedance of the load equal minus the impedance of the, the reactance of the, I'm sorry, not the reactance itself. The reactance here value should be negative the reactance here. Or when you add them, they cancel each other. So we say it in mathematical way. We say we need that the load equal the conjugate of Thevenin. What does it mean conjugate? It means changing the sign of the Thevenin. So if Z Thevenin equal to R Thevenin plus JX Thevenin, so for maximum power, you need the impedance of the load equal the conjugate. What does mean the conjugate? Means you write R Thevenin as it is, but you change the sign of the reactance of the, that will be ZL for maximum power. So when you add them, imagine now we have the circuit. You have E Thevenin as it is, and then you have the impedance of Thevenin, R Thevenin plus JX Thevenin, and then you connect the load, and the load for maximum, you will have R Thevenin minus JX Thevenin. So these two reactances, they are equal in magnitude but opposite in the sign, so they will add, you will cancel. So you have in the end, the circuit has like only resistance, like in resonance. So the total resistance in this circuit, or under this condition, it's equal R Thevenin plus R Thevenin, only resistance. So you have 2 R Thevenin when you add it. So if you want to find the current in this case, I will call it I maximum, in this case, will be equal E Thevenin divided by 2 R Thevenin, right? And they will be, of course, in phase with the voltage. So that will be the current. If you want to find the power, how you find the power absorbed here by the load, okay, how you'll do that? Remember that this is R load is equal R Thevenin now. So this is the load. So the power maximum absorbed by the load, you can say I squared times R. I maximum, magnitude of course, squared times R. And the R is R Thevenin. And this is the current. So as a magnitude, you can write I, the current magnitude is equal E Thevenin magnitude over 2 R Thevenin. Of course, R is only magnitude. So let's go back to the expression. Power equal I squared times R. And I is equal E Thevenin divided by 2 R Thevenin. What is that? That's current. That's the current here. This expression, they just mark it red. This is the expression for the current. Current, somebody asking, why 2 R Thevenin. Divided by 2 R Thevenin. Because you have R Thevenin, R Thevenin. You're adding that 2. All right. Now, you need this current to be squared times R Thevenin. So you will have E Thevenin magnitude square. Remember, all these values root mean square, not max. And 2 times 2 is equal 4. R Thevenin square will be R Thevenin square multiplied by R Thevenin. So R Thevenin cancel with the square down. So we left only R Thevenin on the bottom. So we have E Thevenin square, that's the magnitude, remember, divided by 4 R Thevenin. And that will be the maximum power. So in our example, if you want to find the maximum power, we got to look for the Z Thevenin. You don't look at the load because you choose the load to achieve the maximum power. Z Thevenin is equal to 3, that's Z Thevenin. Okay, let me just show you here. This is 3.9 minus J 3.1. So let me write that. In our example, E Thevenin as a phasor will be equal to, we got it 80 on angle 93 degree. That's what we found. And Z Thevenin, we found it in Cartesian form, 3.9 minus J through 0.1. Oh, to find the maximum power, I'm going to apply this formula. So I'll say P max equal E Thevenin magnitude. So the magnitude of E Thevenin is only 80. I don't care about the angle. So 80 squared divided by 4 R Thevenin. Where is R Thevenin? This one. And you calculate the maximum power. I will let you calculate this one. In watts. So that will be the maximum power. Very simple, very easy. That's it. I think we cover the application of Thevenin with AC circuit. So if you have questions, go ahead and ask me. All right. Bye.